All right, let's get started because everyone's already quiet. So. Okay, so.
One second. Unmute. All right, there we go.
Okay, so we're here for Michael Calzadilla's thesis defense. So I'm just gonna spend about 5 minutes bragging and kind of building him up before we get started. Michael's gonna show you some really nice results, and I want to just talk about a little bit of how we got to those results. So Michael's a real sort of multi-wavelength guy. So the plots you see today are going to come from about a dozen different telescopes, including 170 observations with Chandra, totaling 1,250 hours, or 4.5 megaseconds, if you count that way. There's 53 orbits of Hubble data in here in an obscure ramp filter mode that almost nobody uses except Michael and I. 134 hours with the radio telescope, the Australian Telescope Compact Array, 2 gigahertz data in here that Michael handled for this project. And then about 100 hours or 11 nights of Magellan time from back when we used to go to Magellan and sit there all night. And so we've had a lot of really good times there. And Michael, reduced all those data for this thesis. He's developed pipelines for each of these telescopes individually, so he has a really nice Chandra pipeline that all these data came through, a radio pipeline, an optical spectroscopy pipeline, and we were hoping to lean on a colleague to develop the multi-object spectrograph pipeline, but he was too slow, so Michael stepped up and developed a fourth pipeline to reduce the multi-slit spectroscopy so that he didn't have to stay for too much longer. And do that. So all this is to say, he's done some really good work. This was a pretty heavy lift doing this project, and he managed it really well. Before coming to MIT, he won a pile of awards, which I won't name, but a couple of them were, he had the Gates Fellowship in Cambridge, and he actually won the NSF GRFP before coming here as well. We lured him here with the Fred Kavli Fellowship. And then while he was here, he became one of NASA's finest, the finest or finessed fellowship, however you want to pronounce that.
Both ways, yeah.
And then just last year, he won the Sergio Vasquez Prize, which is a prize we give to a Ph.D. candidate in the physics department who has done great things, but also done great things in the face of a lot of barriers. And Michael had a lot of barriers to get here today that he's just smashed down along the way. The most recent and bittersweet award he's won is the Hubble Fellowship at the CFA. Bittersweet because it means he has to leave, and he's not going far, luckily. And I think we should be able to lure him back if we keep getting ice cream cakes from time to time. So Michael's really good at science and math and these things, that we're supposed to be good at to get these degrees. But the reason that he has all these awards is because he just really wants to be an astronomer. He's really passionate, and he has just a ton of internal drive and desire to make this happen. And so, that's why he's been successful, and why I have no doubt he'll go on to do great things. And so, I'm really looking forward to this talk. It's been a real pleasure working with you for however many years this has been, and I'm looking forward to many more years and many more empanadas and more Cuba Libres on the road.
The empanadas are gold at the observatory. It's currency. So yeah, thanks so much, Mike, for that really awesome introduction. So I think Mike has a lot of potential dirt on me that he could have used to embarrass me, but thank you for making me look good. And I also thank you all for coming and being here today and on my last day of work. And so it's not for now. for I'm going to talk to you about my thesis today about the evolution of supermassive black hole feedback in galaxy clusters. So this just covers a very small topic of how the universe came to be. And so how it started, we've been accumulating data, not just me, but people over many centuries. How does the universe work? We've been trying to understand this. But the story so far, if this advances. All right, the story so far. In the beginning, the universe was created. This made a lot of people very angry, and it was widely regarded as a bad move. This is just, I think, a fun quote from Douglas Adams for the Hitchhiker's Guide to the Galaxy series. And I think it also maybe reflects the mood I was in when I was stressing about making a talk. But I think this is really fun because it's really fun, but also it kind of skips over a lot of detail, right? The universe was created. So let's just start from the beginning. It all started with a bang, right? At the first, the universe began with a bang, and then a really rapid period of inflation. Space started expanding so quickly that eventually it started to cool down and allowing for atoms to form, molecules to form, and so on. And then you start getting stars, and so on. And then those stars coalesce, and they come into galaxies. They come together in galaxies. Galaxies can also coalesce, and they come together into galaxy clusters. So they form this really intricate cosmic web of structure. So we look out, plot all the galaxies that we can see in our universe. They form this really nice filamentary structure. And every node, every dot you see here is a galaxy, and these nodes you're seeing the center that are coming together. These are galaxy clusters of galaxies, as the name implies. So I really like simulation. This is a simulation, by the way, and I really like simulations like this because they show that not only the vast technological advances we've made to be able to make really complicated simulations like this, but they also represent a culmination of decades, centuries, millennia of understanding about our universe that humans have been trying to come up with over time. So astronomers come with a lot of physics included in these kinds of simulations. So they are trying to recreate what we see today. And so that's what I really like about astronomy. So as Mike was saying, being an astronomer, what really compels me is being able to ask and also to answer these really big questions about our universe. So like, how did we get here? One fun example of this is like the eclipse that happened a couple weeks ago. So a couple of us, we did a road trip. I hope people got the chance to see this, but it was a really incredible event. And I get it, like after seeing it, right? So centuries ago, people would see eclipses like this, these cosmic phenomena, be like filled with terror, like what is going on in the sky? But when you get understanding of it, you're less afraid of it. So we've always been looking up to the skies and trying to kind of figure out our place in the universe. How did we get here, to explain things around this? We know that the moon is covering the sun here, and that's what an eclipse is. It's not like a big snake swallowing the sun. But now we are asking some deeper questions. So if we go out into the universe, for example, what else is out there? If you look at this tiny patch of the sky, for example, so this tiny patch of the sky compared to like the size of the moon that's covering the sun here, and you park a telescope, one of our best telescopes that we have, the Hubble Space Telescope, you park a telescope and just watch that spot where it looks like there's nothing for about 10 days. Things start showing up as these exposures kind of accumulate. So what you see when you zoom in on this, what Hubble saw, this is called the Hubble Deep Field. This is 10 days of observation. And what it shows, every single dot that you see here, except for like this thing and that thing up there that has these spikes, those are stars. Every other dot you see here is a galaxy. And this is incredible. You see a huge variety of galaxies. If you zoom in, you see things like spiral arms, these spiral galaxies. You see things that are more kind of ball-shaped. You see blue things, red things, yellow things. There's a huge variety of galaxies. So how did we get here, right? Another interesting thing about this is you're not just seeing different shapes, sizes, colors, and all that about galaxies. You're also seeing different times, right? You're seeing different aged galaxies. So this picture is more than just a picture, right? It's a cross-section of the entire universe, basically. So when we look at, because light takes some time to get to us, the light that's been coming from things that are very far away, those are older things, right? So if we have, when you look at pictures like this, a mix of young things and a mix of very old things. So this is, the state of things as we know it. So this is how we think the universe evolved. My thesis is concerned with this later part of stuff, which is how did galaxies develop? How did they become what we see today? So you don't have to worry about the stuff from before now. You can just get that out of your mind. So they come in lots of shapes and sizes. But broadly, we can say that these the garden variety galaxies, you're either like red and dead elliptical galaxy. There's not a lot of star formation going on. There's not a lot of gas in these galaxies, and so you don't have a lot of star formation going on. Spiral galaxies like our very own, this is the Andromeda galaxy, it's our nearest neighbor, has a lot of gas and a lot of material to work with to form stars. So how did we make these? How do we arrive at either a blue star forming galaxy or a red and dead galaxy, right? And the answer lies within the galaxies themselves. There's something that's really hard to see, but if you take this video here, and I think I'm going to speed it up because it goes through quite a bit. This is the center of our Milky Way. If you had a really clear sky sometime, if you're lucky enough to see the Milky Way, this is really beautiful. But if you can zoom in with really good telescopes, you see lots and lots of stars. There's lots of dust. All this brown stuff you're seeing is dust. There's lots of stars as you're zooming in. You can keep going towards the center of our Milky Way, and you see lots of really yellow, blue stars, all different kinds of stars as well. But the important thing here is that as you keep zooming in, you can now look at these stars and kind of track their motion over time, right? So if you start tracking their motion over time, you see some of them look like they're whipping around, right? They're making these orbits and going these kind of circular elliptical orbits. They're circling around something, and that something, we think, is a supermassive black hole. So this is a little illustration, but I think so supermassive black holes, as I'll show you in the rest of this talk, have a really big influence on how you get these yellow or blue galaxies. I'll show you how they do that, but so with that teaser there, I was just launched into this, the outline of my talk. So I've just given you kind of the motivation, but I'll be telling you now in the first part of this talk, this background that you need to understand how exactly do black holes shape their galaxies. And then I'll be going on to what are the limits of how these black holes can shape their galaxies. How much damage can they do, basically? And then once we understand things really well in our neighborhood, how these black holes do this, then we can actually move forward and understand how has this whole process evolved over time. So first, I just want to say, galaxies are not closed boxes, right? So you saw the video that I was showing you before, all these bits of gas and stars forming galaxies, and the galaxies are merging together. Stuff is coming in all the time. These galaxies are kind of stripping gas off each other, and stuff is being exchanged all the time. So a galaxy is not some impermeable membrane. It actually there's inflows all the time, and there's outflows from various processes, and that's what we're going to be studying. But this whole thing we call the baryon cycle. So the baryon is just like matter. How is matter cycled in and out of galaxies? And so we're going to call the atmosphere of a galaxy the circumgalactic medium, or the CGM, and I'll be telling you about the various processes that actually cause these inflows and outflows. So to be able to see this entire baryon cycle, how galaxies do this evolution, we need to look at beyond what human eye can see. So how do we see the universe? When you're looking around right now, you're using the optical part of the spectrum, but you can see light. It's light. Light comes in very many, really big range of frequency and wavelengths. So what you can see with your perceive is just this narrow range here, but you can see there's so much more. These are orders of magnitude, like factors of 10. There's so much more above and below those wavelengths that we can physically perceive. So we have to be really clever, and we've made lots of telescopes over the past century or so to be able to exploit these different wavelengths to learn even more about the universe and how these galaxies evolve. So I, for my thesis, have used all these different, there's a lot more telescopes that cover this range, but these are telescopes that I've personally used in my thesis. So these are just to introduce them, because you're going to be hearing about them a lot later. The first one here is Chandra on the left, which gives us access to the X-ray part of the spectrum. Then we have Hubble, Hubble is here, which is in space, and then the Magellan Ground-Based Observatory. It's this really nice picture here you see on the wall that Mike and I have been to several times and collected data for this thesis. The South Pole Telescope, which allows us to find galaxy clusters at microwave wavelengths. And this is the ATCA array, which allows us to see things in radio wavelengths. So what I look at with all these telescopes is galaxy clusters. So galaxy clusters, you'll hear any galaxy clusters talk start with the same sentence. They're the largest objects in the universe. They're the largest gravitationally collapsed objects in the universe. As such, they have, by what it sounds like, lots of galaxies clustered together. So galaxy clusters have hundreds of galaxies often. They're dominated by one really big, brightest cluster galaxy at the center. So we saw how galaxies are merging all the time, and eventually you can get really big galaxies like this kind of pooling together galaxies, right? So that's what we call a BCG. And there's a lot of mass contained in galaxy clusters, 10 to the 14 to 10 to 15 times the mass of our sun, for example. There's a lot of mass, so that's what that symbol means. You're going to see it a few times throughout this talk. It's the solar masses. Just putting in units of how much how big our sun is. But most of the mass is not inside these galaxies themselves, the stars that make up the galaxies. Most of the mass of galaxy clusters is actually in the space between all the galaxies, which is what we call the intra-cluster medium, or the ICM. This is a really hot plasma that makes up most of the luminous matter, and it glows in X-rays. It's really hot, 10 to the 7 Kelvin, so it glows in X-rays. You get things like radiative cooling. And the important thing I want to note here is that the intensity of these X-rays, how many X-rays are given off that you see here, that you observe with telescopes like Chandra, is proportional to density and inversely proportional to temperature. So when you're looking at this image right here, as you go towards the center, towards that BCG at the center, you're getting brighter and brighter in your X-rays. And what that's telling you is, in turn, you're getting a colder and denser core. right? So that cold, dense core, the cold, dense material becomes so cold that it starts cooling out of the X-ray phase, it becomes multi-phase. Then you can see it in UV, then you can see it in optical wavelengths, and so on. So it keeps cooling until it hits the galaxy at the bottom of that gravitational well. So because BCGs are at the bottom of this really deep gravitational potential, you should expect really high star formation rates in BCGs. They should be the bluest, the brightest, most star-forming galaxies in the universe. But when we observe them, in fact, they're what we call red and dead. They're these really yellow, passively evolving elliptical galaxies that aren't doing very much star formation at all, right? So to put that in a little bit more concrete terms, if you were to take all of that gas that you see in X-rays and cool it down into the center, you can measure that, what we call a cooling rate. So that's going to be here on the x-axis in terms of solar masses per year. And then you measure how much is actually cooling in the form of star formation in a central galaxy. That's going to be the y-axis here. The ratio of these two quantities, the star formation rate to the cooling rate, if you measure that for a bunch of different galaxy clusters, they form a distribution that peaks at around 1%. So 1% of that cooling is making it into forming stars. If any of that sounded confusing, I have a much better explanation for this. I just first want to say that since I've moved here to Boston for all my Florida friends, I've been enjoying the snow. And I've really been enjoying skiing. So this picture here on the left is my very first time skiing here in Massachusetts, and I'm on the ground. And I was on the ground for most of that trip. So I haven't gotten too much better, I want to say, but I still rather enjoy it. But if you were to take this Michael that's here skiing and put him at the top of a hill and put 100 Michaels at the top of a hill, let's say. There's 100 Michaels at the top of the hill, and they're all going to start coming down at the same time, right? So they start skiing, they start coming down. Something happens, and then only one makes it out. So what happened to those 99 Michaels, right? So that's how we explain this plot again, except I relabeled the axes now. The axes now are Michaels at the top of the hill on the x-axis, and on the y-axis, Michaels at the bottom of the hill. And only 1% of those Michaels ever make it to the bottom. So what's going on, right? It turns out, we think it's a supermassive black hole. It could be a bear or something, I don't know. But in this case, we're going to talk about supermassive black holes. So as I was saying before, the centers of galaxies, we have supermassive black holes. There's one at the center of our very own Milky Way. It's called Sagittarius A star. And this is we can see this in X-rays. And just to remind you again, this is the data showing that, which won a Nobel Prize, by the way, discovering their black hole at the center of our galaxy. You can see stars whipping around some central object that you can't quite observe directly. And so these black holes, let me just go back for a second and say that we see these stars are all kind of orbiting in these like stable orbits, right? But things fall into these black holes too. And often, when you have, for example, some gas coming in and on a particular orbit that hits the black hole, it forms this accretion disk, and that accretion disk gets so hot it puts out a lot of energy, a lot of light. So despite the fact that black holes being these really dense, compact objects that don't let even light escape, this makes the accretion disk around the black holes some of the brightest things in the universe. So this is what we call an active galactic nucleus, or an AGN. And from now on in this talk, I'll be referring to the whole region, a black hole, its accretion disk, and its energy output as an AGN. So just so you don't get confused, AGN equals black hole, basically. And these black holes are often messy eaters. So they spit out their food a lot of the time, and so in the form of these relativistic jets. So they coil up the magnetic fields of the really hot plasma they're accreting, and these jets get collimated and launched outside away from the black hole. And these jets have a really big impact on the galaxies that they're hosted in. So I'll be telling you about that a bit more. But for now, I just want to say this is an artist's depiction, and it's really cool. But even cooler, I think, is an actual picture of a black hole, which we got a couple of years ago. This is from the Event Horizon Telescope collaboration. So this is at the center of the Virgo cluster. This is a galaxy M87. And just for context, this is a really massive black hole. But just for context, if you were to take our entire solar system, so let's say the outside orbit of our solar system, let's use Neptune as an example. If you take the sun and all the way out to Neptune and plot it at the same scale as this black hole, you can see that we'd be engulfed by it. It's a really massive black hole. It's 1 billion times more massive than our sun. And what I want to show here is that this is using the Event Horizon Telescope. This is a really long, very long baseline interferometry technique. But if you can zoom out and use various different telescopes, you can see this jet too in actual data. As you keep going further out, you're zooming out. You're seeing the jet still in radio, and then you start to see it. It's so energetic that it becomes visible in optical wavelengths as well. And then you're seeing here how this jet extends far beyond the host galaxy that it's in, and then you can see kind of the surroundings. You're even seeing these jets in X-rays. And so I just want to highlight the fact that despite black holes being this really tiny thing compared to the host galaxy, they have this really huge impact. The jets can go on for very much far beyond the galaxy itself. And that's how we're going to build this notion up of how black holes affect the evolution of their host galaxies. So these tiny things can have a really big impact. So these jets, they launch and they interact with their surroundings. So this is a simulation of a jet going through their surroundings. And you can see here that it's kind of driving a lot this kind of turbulence and stirring things up. And it kind of creates this bubble that starts rising buoyantly out of the potential. This is very similar, I think, to if you've seen Finding Nemo, or not even Finding Nemo, but if you have ever seen a fish tank, you have like a bubbler at the very bottom. You have this bubbler that aerates the air, distributes oxygen into the water for the fish. The same way, these AGN are distributing energy, their accretion energy, and converting that into this outburst energy that then aerates kind of the surroundings, and that's how they kind of couple their energy to them. We see this in a few different places. For example, our Milky Way, we have evidence that there was some outbursts in the past. These are what we call the Fermi bubbles that extend really up far above and below our galaxy, which Tracy here on my committee helped to discover, which is really cool. And I also, another cool example is the closest AGN to us, which is called Centaurus A. And here you're seeing a multi-wavelength image, an optical and radio and X-rays as well. You can see the jets and the galaxy is in the center there. And I'm pointing this out because I want to just plug really quick how we had a study on this that was then featured on the cover of Nature Astronomy a couple years ago. And this is using data that I featuring data that I collected from my first successful proposing run in this Hawaii observing school at Mauna Kea. So that was really cool. I really enjoyed that. So yeah, you can look at a galaxy and think it's a pretty unassuming thing. So this is another galaxy, Cygnus A, and optical wavelengths. So this is thing in the center. But when you look at it at radio wavelengths, you can see the jets. And these jets extend far beyond the galaxy, right? You can look at it also in X-rays, and you can see these jets are visible in X-rays too. But most notably, I want to point out that there's these big holes in the emission. It's like these shadows that look kind of, and that is perfectly anti-correlated with the jets that we see in the radio. So these jets are actually pushing material out of the way and carving it out, excavating holes and cavities in this X-ray emission. So the bubbles in radio are the same thing as cavities in X-ray. And these are really useful things to study because if you can, but first I want to say, just for scale, these bubbles are really massive. So we can take 6 Milky Way-sized galaxies and fit them inside one of these bubbles, for example. But these are really useful things to study because they help us figure out the energy of an AGN outburst. If you were to take these jets, you're plowing through this medium and you're pushing it around, you're compressing it. They're kind of acting like pistons. So you're doing mechanical work on your surroundings. So by measuring the pressure of those X-ray gas around those cavities and the volume of them, you can estimate some kind of energy associated with that outburst. If you measure that, you can compare it to how much energy is associated with the cooling that's falling onto the black hole. So the output versus the input. You see these are very strongly correlated. So here on the y-axis, I'm showing you cavity power, so cavity associated with the AGN outburst. X-axis, I'm showing you cooling luminosity, so power associated with the cooling that's falling onto the black hole and feeding it, right? You can see it's kind of like this really tightly regulated feedback loop. If you dump a little bit of material onto the black hole, you output a little bit of energy. If you input a lot of cooling material onto the black hole, you output a lot of energy too. So it's a really tightly regulated thing. And so in that sense, I think it's really fun to point out, I will leave this outstanding questions for later. I think it's really fun to point out that AGN feedback act as this kind of cosmic thermostat, or they regulate this cosmic thermostat. So they're really kind of like the cosmic dads that are telling you that don't like you touching the galaxy thermostat, right? So this is, by the way, an astronomer, Fitzwicki. He's a spicy guy, character he was. So you would like your temperature in your room to be 100%, to be a certain temperature. You would like the cooling to be 100% efficient, but to save money, you're cranking it down to 1% because the black hole doesn't want you doing more than that. So that's a bit of, I think, a good analogy. So, and just to tie this all together, how this whole process works, now that we've seen, we can look at different wavelengths and really use those to our advantage to see this entire baryon cycle happening in galaxy clusters. If you take the ICM of a galaxy cluster, you can just model it as like a big ball of plasma, a big ball of hot gas, and you have a black hole at the center, and these are not to scale, but this is just for illustrative purposes. If you take all that gas and you contract it, you cool and you contract at the same time. If you cross some kind of thermodynamic threshold, which I'll tell you about later, eventually you start cooling out of the X-ray phase and depositing onto your central galaxy, which fuels star formation as well as feeding onto your central black hole. Eventually, this black hole could outburst, shoot out these jets of plasma that couple energy to their surroundings, and this energy being coupled to their surroundings heats it up, and then the black hole basically starves itself, and then the cycle is allowed to happen again. So this is the AGN feedback cycle. So just to tie that all back together, these black holes are really strong engines of recycling of material in these galaxy clusters. So when we look out into the universe and we see a bunch of different types of galaxies, we might, from theory, we expect this red line here I'm showing you here. So what I'm showing you here on the right-hand side is this galaxy luminosity function. What it's really just telling you, all of it, it's very simple. It's just telling you how much of something there is. So you have small dim galaxies on the left-hand side of the plot and big bright galaxies on the right side. And what this is telling you is that you have a lot of really small dim galaxies and a little bit of big bright galaxies. But what we actually observe is much fewer small dim galaxies than expected and much fewer big bright galaxies than expected. I've just been talking about this right-hand side of the plot for the biggest, brightest galaxies that we know of, which is the BCGs. And what's driving this discrepancy, this suppression of large galaxies, is AGN feedback. So with that out of the way, this is all kind of stuff that we knew up to this point, right? So I'm going to be talking now about what my contribution has been to this whole idea of AGN feedback and how that shapes galaxy evolution. So I'll be talking right now about the limitations of this feedback cycle. What can it do and what can't it do, right? We want to be able to understand that really well before we start probing the uncharted waters of high redshift of the early universe. So I've shown you this plot already. This is AGN power versus cooling power. And we said that they're very strongly correlated. So this is telling us there's a very tight feedback loop. It's a really strong cosmic thermostat. If you just turn that around a little bit, flip it around a little bit again, you see that most things, that was completely unnecessary, I know. But I just want to just illustrate this point that most things fall right here in the middle. In the middle, you have a balance between heating and cooling. Things that are above these diagonal lines are heating dominated, and things below these diagonal lines are cooling dominated. But most things lie somewhere in the middle. I'm going to tell you very briefly about things that are heating dominated. So to do that, I want to tell you about one of the early papers in 2019, where we studied this object called SPT 0528 for short. This, just to mention again, was discovered by the South Pole Telescope in Antarctica. I'll tell you more about that later, but the point of this is the South Pole Telescope, or SPT, allows us to find galaxy clusters that are very far away and very early in the universe. But keeping that in mind, we found this really distant galaxy cluster that was discovered with SPT. And the notable thing about this is when we cross-checked it with some radio catalogs, it was one of the most radio loud clusters in this SPT sample crossed with that SUMS catalog. And what this means is that, so radio loudness is just how intense the radio emission you're seeing from it is. And so we know that when we look at pictures like this, what I was telling you already, that these radio jets, in radio you can see these jets that really kind of could distribute energy and material and so on. So because it's a really radio loud cluster, we might expect there to be really powerful jets. So that's what we searched. That's what we went to search for. So here we're seeing now the same system that was showing you optical wavelengths before, but now we're seeing at X-ray wavelengths. We see that there's these two big depressions here. It's a bit of a noisy image, but this kind of corroborated by the fact that in radio wavelengths, which you see on the right, we're seeing different frequencies radio data that's showing you kind of a direction of a jet. So this is kind of leading some credence to this cavity scenario. If you were to take these cavities, assume they're real, and measure some power associated with them, these numbers don't mean anything to you, but it's really powerful. It's on the order of the most powerful things we've ever seen, right? The most powerful AGN outbursts we've ever seen. And here I just want to say that it's kind of unnecessarily powerful. The energy per particle in this system is 600 eV, which is much higher than anything else. But more importantly, I want to say that this is unnecessarily powerful feedback. So if you were to take the cavity power, so this is again AGN power, compared to the cooling power that I've been showing you a few times already, the ratio of those is about 1, right, for most systems. So you can see if you plot things here on the right, the ratio of those two versus redshift now, we see that most things kind of scatter. There's a lot of scatter, but scattering about 10 to the 0, which is 1. This system that I've been telling you about now, SPTO 528, is this bright star, this blue star here up in the top right of the corner. So this is almost 100 times, the ratio is almost 100 times, which means it's acting like a really faulty thermostat. So if you were to take the temperature in your room and cool it down by 1 degree, the response of the thermostat in this case would be to crank this heat up by 100 degrees, right? So that's just not ideal. So the AGN SPTO 528 is like a faulty thermostat, but this thermostat can break in other ways too. So we're also going to cover the case of cooling dominated feedback. So that's the next part of my talk. We're still covering the extremes of feedback, but we're going to talk about what governs the effectiveness of feedback. How effectively can it suppress cooling? So I was showing you this before. This is the Michael's in versus Michael's out plot. So here, what we're showing is that most things, on average, lie on this 1% efficiency line. That's this comfy set temperature for galaxies in galaxy clusters, BCGs in galaxy clusters. You might notice that there are a few things that lie quite a bit above this line, though. So here, the systems that I've circled here, these data points that I've circled here, are about 10, 20 times more efficient, cooling 10 to 20 times more efficiently than all the rest of the systems on average. So what's going on here? So Mike and I, we got a really big Hubble proposal to study these systems, these extreme cooling systems, to figure out why is AGN feedback struggling in these systems to suppress all that cooling. Why is it allowing more cooling to happen than in any other system? And for he was alluding to before, we use this really obscure ramp filter on Hubble to map out ionized gas in the form of oxygen-2 emitting multi-phase nebulae to investigate why is AGN feedback struggling, and also why this is a very recent finding, which is AGN feedback, I've been telling you, could suppress cooling, but it can also promote cooling locally in some cases. That's just going to be a wrinkle in the whole story, so I'm not talking about point 2 for today's talk. You can ask me about it later, though. I would be happy to talk about it. But just because of the time, we'll just talk about point 1. So here's our sample that we studied with Hubble. We also have Chandra data on each one of these systems. It's a lot to see, but I'm just going to guide your eye a little bit, zoom in on one of these. This is called the Phoenix cluster, which was also detected by the South Pole Telescope. But on the left 2 panels, we're seeing data from Hubble. So here's this kind of broadband, really large filter collecting data across many wavelengths, image of this galaxy. And then in the middle, this is using a very narrow band filter to kind of isolate just oxygen-2 emitting gas, basically. So we did some fancy modeling to be able to get these maps out. So what you can do here is just basically draw a big circle around it and measure how much light, how much flux is coming in from this nebula here. And so we kind of remake the same plot that I've been showing you. Again, Michael's in versus Michael's out plot. And so here, we plot our new systems as well as literature data and kind of homogenize for a bunch of different factors to kind of control for various things that are pretty heterogeneous in the literature. So we try to do a little bit more carefully and with just very certain star formation indicators. But you can see, again, if you just take an average slope through these points, a constant slope of 1 through these points, you have, again, this 1% suppression, 1.3% suppression I've measured here. But you can see pretty clearly that most of these points don't really lie on this. It looks to be like it isn't quite a good fit. So if you were to take all of these points and then instead just batch them into different cooling rates, so things that have from 10 to 100 solar masses per year in cooling, then 100 to 1,000 are going to be shown in green, and then above 1,000 solar masses per year in cooling, that is cooling, is going to be shown in red. You can see that they kind of increase as you go towards higher cooling rates. So these histograms are just showing you the average, the distribution of the ratio between star formation and cooling rate. And you can see that as you go towards higher cooling rates, so from bottom to the top, the histograms are moving to the right, which is telling you, if you're increasing the amount of material you're piling onto your black hole, you're cooling more of it is going into forming stars, and less of it is being suppressed. You could do a much simpler, even simpler thing and just fit a line through all of it. We find a steeper than unity relation between star formation rate and cooling rate. So what this is telling you, there's a gradual increase in the cooling efficiency of these systems, which could conversely be interpreted as a gradual decrease in the effectiveness of feedback instead. So one way to understand this, if we consider the relative growth rates of these black holes that are sitting inside of these big reservoirs of hot plasma, the ICM, they should grow proportionally using some simple scaling relations. for those who don't know, black holes have a limit on how much they can feed. It's called the Eddington limit. You can only push so much onto the black hole before the energy being released in the accretion pushes away that material. So light has pressure, it turns out. So this is called the Eddington limit. And based on this proportionality, the growth rate of a black hole has a cap, whereas the growth rate of the ICM, the halo that it's embedded in, has no analogous cap. So you're growing proportionally for a period of time, but if you, for example, accrete some smaller subhalo, smaller galaxy with a black hole in it, the halo, the ICM will grow a lot faster than the black holes will be able to merge. This could lead to undermassive black holes, for example, and this would affect their mode of AGN feedback. So I've been telling you about AGN feedback and how it suppresses cooling. There are a few different ways it does that. So to illustrate that, I have two identical galaxy clusters. By that I mean the same size and amount of ICM here, and I'm plopping two black holes in these identical halos. So one black hole on the left, we'll call it proportionally sized, and the black hole on the right, we'll call it undermassive. So what I was telling you before, if you dump some amount of material onto the left black hole, it's going to reach some small fraction of that cap, that Eddington cap that you can't go past. And if you plop that same amount of material onto the undermassive black hole, you're going to have the same accretion rate, but it's going to be a much higher fraction of the cap, right? So because of this, you're going to have different modes of AGN feedback. On the left, you have what we call radio mode feedback, where these jets that I've been telling you about get launched and they heat up their surroundings. And on the right, it's more radiation-dominated feedback. And we think that the radio mode feedback, the scenario on the left, is more effective at suppressing cooling than quasar mode feedback that you see on the right. So both prevent cooling in their own ways. So quasar mode feedback can prevent local cooling, but they can't quite prevent all that cooling from getting dumped onto the galaxy, the host galaxy itself. So a lot of it gets pooled together into the galaxy and forming a lot of stars. Whereas on the left, radio mode feedback kind of stops the cooling at larger scales. So you can suppress a lot more of that cooling from actually reaching your galaxy in the first place. So the takeaway here is that radiatively efficient quasar mode systems, like the one on the right, allow for more efficient cooling of hot to warm gas, so from X-rays down to optical wavelengths, basically. So it's no coincidence, I think, that when we look at this plot again, the most efficiently cooling systems that you're seeing here on this plot, which I've circled in red, they're also our only quasar systems in our sample. So this is probably telling us that quasar, if it's in quasar mode, it's not able to suppress as much cooling as if you were in radio mode. Yeah, so I mean, going back to this analogy of the thermostat again, in this case, it's failing because if you imagine being in the middle of winter and you open up all your windows and your doors and you let all this cold air in, your thermostat and you leave your heater on, is only going to be able to do so much. It's going to try to keep up with it. Even in the presence of feedback, there's evidence of it trying to keep up with all this cooling, but it can't match how much is being dumped onto it. So that's what's going on here. So we think AGN feedback is struggling in these systems that are really strongly cooling because there's maybe different modes of AGN feedback occurring. In the second part of this talk, I also of this paper. It's a really big paper, but I address how feedback can actually promote cooling. And it turns out there are various different indicators that can predict where multi-phase gas should occur. So this is a bit of a summary for that section of my talk. So we got a lot of new Hubble data to map out warm ionized gas in the most strongly cooling systems. And we think that, and we see that hot gas is converted to warm gas much more efficiently in systems where there's really strong cooling rates. So there's implying a gradual saturation of AGN feedback that might be linked to the mode of AGN feedback. And this part I didn't really talk about, but I just want to have this bit of a segue here, which is that these systems could represent a very low redshift or nearby universe window into high redshift or early universe phenomenon. And so that's kind of going to lead us into this next part of our talk, which is the evolution of feedback. Now that I think we've understood feedback, the nuances of feedback in a bit more detail in the nearby universe, now we can then move on to trying to figure out what's going on in the high redshift universe, is uncharted territory. So how has the cooling feedback cycle evolved? Well, first of all, it's really natural to ask, why do you expect it to evolve at all, right? So I've showed you videos like this before where things kind of start coalescing and galaxies start merging and being bound to each other. So in the early universe, this was happening a lot more often than in the present day universe. The universe had its foot on the gas pedal early on, and it's kind of let off since then. But as you go towards higher redshifts in the early universe, you have higher rates of galaxies being in mergers. You have a higher availability of gas. The cosmic star formation rate on average was higher as you go towards high redshifts, so it peaks at around a redshift of 2. And I think this is handy too. So if I'm talking about redshift, I'm also talking about time and look back time and distance. So this is kind of, it peaks at around 10 billion years ago, which is kind of the range of redshift that I'm studying in my thesis. So as you're going towards this upper range, you might expect higher star formation. You'll expect higher star formation rates, more gas. We also know that the quasar fraction increases as you go towards higher redshift. So the mode of AGN accretion that I was telling you about, quasar mode versus radio mode, quasar mode means you're accreting a lot more rapidly. So the growth of black holes did most of their growth at early times compared to the present day. Some notable examples of extreme cooling at high redshift is this galaxy cluster that I didn't study, but it's called Sparks 1049. Very high redshift, and there's a lot of star formation happening in this system. But the interesting thing here is this: if you look at it in X-rays, you see that where this cooling is happening out of the hot plasma is kind of localized in this really bright blue spot here. And that, you might notice, is kind of happening in a random place. Like there's a galaxy nearby over here, but it's not quite here, right? They're not centered on each other. So this might be telling us is that there's cooling happening in the absence of feedback, because the black hole that would provide the feedback is not centered. The galaxy isn't centered on the cooling. You might expect eventually that through like dynamical friction, that these galaxies then fall to the bottom of that gravitational potential and ignite cooling eventually. But that's all to say that we think AGN feedback should have a time when it starts, right? There should be a start time at some point. So hasn't been happening since the beginning, perhaps. So another notable example is this galaxy cluster I studied called SPT 2215 that we also found at the South Pole Telescope. And just, I want to go through quickly for this, but it's an exceptionally isolated and relaxed galaxy cluster with a lot of star formation going on. And here's all the data we have on it. We have radio data, which you can zoom in. You can see there's an AGN by the radio data. You can then zoom in and see the galaxy cluster, the ICM emission in X-rays. So this was found because it was a really extremely relaxed galaxy cluster in X-rays. So it's very, very symmetrical. If you had a system that had a lot of merging going on, it would not look like this. It would be very disturbed morphology. But the fact that it's very relaxed tells you it's been parked doing nothing for a while, basically. Just like residual cooling is happening. So because it's extremely relaxed, we measure the thermodynamics of it, and we see that it has a really strong cool core, which means this material in the center is cooling very rapidly. So because of that, you should expect all that cooling to be deposited into your galaxy, and you should see a starburst, like what we do observe. So just like the extreme cooling systems I showed you with the big Hubble program we studied, there were all these filaments going on, and it's really shallow, like half an orbit data of Hubble. We can see kind of this structure, like filamentary material, this wispiness here. With any deeper data, it would surely show something really spectacular. So these are star-forming filaments where stars are forming. And this is what these raw data look like. This is a spectrum. This is just light being split up into various different wavelengths. It's kind of like a barcode for what a galaxy or star or whatever is made out of. By separating its light, we can figure out what it's made out of. And this barcode here is telling us that the wavelength of this certain element, there's a lot of emission going on. So that's what we look for to see if the emission of this particular wavelength is telling us that there's star formation going on. So by modeling this spectrum that we see, along with some various measurements from different telescopes, we can then look for the presence of this emission line, we call it, of oxygen 2. And this can be converted into a star formation rate, which we estimated like at 300 solar masses per year, which is really, really high. And if you compare that to how much you see cooling, again, how much material is poured onto it versus how much you actually see star forming, it's really highly efficient on the level of the really extreme clusters that we saw before, which is kind of weird because there's evidence of AGN feedback. There's a radio source, but in this system, cooling is a lot bigger than heating. It's usually around 1, and here it's about 1/10, right? So maybe this is a recently activated AGN, like we were saying before, like in this system here, where initially you don't have your cooling funneled onto your galaxy, so there's no feedback. Eventually, maybe it coalesces then feedback can start. Maybe that's what happened in this cluster, but we don't really think that because it's way too relaxed. It looks like it's been sitting for a long time, and instead it looks like this Phoenix cluster, which is the most star-forming, most relaxed thing we know of, but at double the redshift. This is like a redshift that corresponds to like 9 billion years ago. So it had to have been sitting for a long, long time. It had to form really rapidly and sitting there for a long time doing nothing, basically. So these have kind of interesting implications for the evolution of how things worked in the past. And they're insightful clusters, insightful systems, but they're not representative. So we've talked about these extremes of cooling and heating already, but most systems we've said they have a balance between the two. So we need to look at large statistical samples for evolution because we can't really quite measure the evolution of a single system. They don't evolve on the human timescales for us to be able to do that. We have to look at large samples and say on average at this redshift, what these systems look like, average and so on along the redshift bins. So as I was saying before, we have this cross-section when we look at out into space, and we have old and young stuff mixed in any observation that we have. But when we look towards higher redshift, so early on, we're also we might be biased in some cases because we can really see just the brightest things in these cases. So if you have really dim stuff here, you have a mix of really dim and bright stuff here in the nearby universe. As you go towards higher redshift, the dim stuff you can't quite see anymore. This is called a Malmquist bias, right? So this is it's very beneficial in some ways, but also it limits us in some ways. In particular, when you want to study evolution of systems, right? We want to be able to account for these kinds of biases. So we use a South Pole telescope to be able to find systems using a different method. So this is using the Sunyaev-Zeldovich or the SZ effect. So this takes the very first light of our universe, the cosmic microwave background, or the CMB. If we take that CMB and the light that comes from the CMB, as it streams towards us, towards our telescopes, then the CMB photons that are really low energy microwave photons encounter the hot ICM, the plasma of a galaxy cluster, they get scattered towards higher energies. So when you look at a map of the sky and using the SZ effect at certain frequencies, you'll see holes wherever those CMB photons encountered a galaxy cluster. So this allows us it's a redshift independent detection of galaxy clusters. To be able to actually find the redshift, how far away they are, you have to follow them up with various other telescopes. But this in turn enables studies of evolution. So here I want to show you the power of these SZ surveys. So this flux-limited surveys that I was showing you before the SZ effect are samples like these blue and red squares here. You can see that they they go up, but they don't reach too high of a redshift. So redshift here is going on the x-axis, but the SZ effect, the SZ-based samples that we use with SPT are going out to really large redshifts, about 1.5 or and beyond, about 10 billion years ago, much further range that we can get with these flux-limited surveys. And so the sample that I focus on in my thesis is the stuff in this red box. Everything in that red box is what I do. And we can do some interesting stuff with this. So we were talking about when does that AGN and cooling feedback cycle start. So by measuring thermodynamic structure of the ICM, it tells us about the susceptibility of multiphase cooling. So this is going to be a trigger. What triggers cooling to happen? You can measure these properties as a function of radius. And when you measure systems that have, you can measure certain thermodynamic properties like entropy, which is just a combination of density and temperature here, but it tells you about the susceptibility of cooling. If you measure that entropy profile, entropy is a function of radius for many different systems. In the systems where you have a galaxy at the center of that cooling that has filaments of star-forming filaments, the entropy profiles reach a very low value go down here, the red curves. And the systems where you don't have this star formation going on, there's no filaments in H alpha detections, they all kind of level off at these really high values of entropy. They don't cross this threshold. So we can call this a kind of arbitrary number, but a threshold here that below which the ICM becomes thermally unstable and becomes multiphase cooling, cools out of the X-ray phase. So this thermodynamic threshold, this entropy threshold, is shown here in two different ways. So again, this H alpha, this is detection of line-emitting gas, which tells you about star formation. You can see that below some threshold, this dotted line here, below that threshold, systems where you measure this from X-rays, below that threshold, you get an explosion of detections of H alpha. Similarly, below that threshold, if you measure that same threshold in X-rays, and you see which systems have radio detection, so we're looking for AGN basically, there's an explosion of detections below this threshold and mostly upper limits above that. So the ICM becomes thermally unstable below this threshold, which triggers both star formation and AGN feedback at the same time, right? So what I want to point out here, though, is that this is a really well-known result, and it's been corroborated many times since, but this is for very nearby systems. This is a redshift below 0.2. And so this hasn't quite been done for high redshift systems, but yeah, I could show this too. So as I was saying before, we have the ICM contracts and cools, and the central entropy falls below some threshold, and then you get stars and black hole feedback. And then these feedback pushes things out, it heats up the atmosphere, and then you have higher central entropies, and then it's not allowed to cool again, right? So what we want to do is put a redshift axis on these two plots and see how has this threshold, if at all, changed with time. To do that, we use what I said before, the SPT surveys. And this is what we call the SPT Chandra sample, because every single system in this sample has SPT data, has Chandra data, and radio data, optical data from various places. So we can look at the X-ray image of a sample cluster in this sample. This is I didn't mention this, but it's 100 galaxy clusters, and they span 10 billion years in evolution. So an example of one of those clusters in our sample is this one here. Here we're looking at it in X-rays. By measuring the thermodynamic properties of it and derive an entropy profile, we can then say in the core of it, how low is the entropy? If it's below some threshold, you expect multi-phase cooling. We can follow, if that happens, we can follow that cooling down to smaller scales and see if it's made it to the galaxy. If it's made it to the galaxy and it's forming stars, this is what I did. I went to the telescope and tried to look for, and got spectroscopy on a ton of different galaxies. What we're looking for is the presence of oxygen-2 emission. If that happens, then we know that there's probably star formation going on. And then we can follow the cooling to the very smallest scales and ask if it's made it to the centermost black hole in that BCG. And here at a glance for our entire sample, you can see if we have radio detections or not. So do we see AGN accretion happening in there or not? And here is our result. So I was telling you already, so below some entropy threshold in the nearby universe, we have detections of star formation, and above that limit, we do not, right? So this has been shown already. This is what we've already known. But what we've done for the very first time is show that this threshold persists out to very high redshifts. And so this line that we've drawn here separates detections from non-detections pretty cleanly, and it's still separating things pretty nicely as you go towards higher redshifts. So I've just kind of drawn this line here. This is based on the low redshift data and just kind of pasted it onto all these. But if you actually try to measure what that threshold is, see if it's evolved over time, I find really no statistically significant evolution in that threshold value. And the fact that these error bars don't blow up, but we can still measure an actual consistent threshold value, implies a very strong, long-lived connection between the cooling and star formation. This is a fun result that earlier this year we presented at a press conference at AAS, which is a fun experience. So yeah, just showing you that again. Here's all the 5 plots of star formation versus entropy. And on the bottom now, I'm going to show you data for the radio side of those plots. So before, again, we see below some threshold, you have ignition of AGN feedback at low redshifts. When you go towards the high redshifts in the last three columns, that dichotomy disappears completely. It looks like there's no real line separating detections from non-detections in those systems. So this is a weird result that we don't quite understand too well yet. I was thinking maybe, so this is implying that there's some strong evolution in the cooling and feedback cycle, and perhaps the feedback cooling connection is not as tight in the past as it is today. Possibly because, as we've talked about, we have, for example, higher merger rates as you go towards higher redshifts. These mergers are bringing in gas to your galaxies, and that gas is also reaching your black holes. So the mergers could be bringing in gas to your black holes, and what that would look like, as I've said before, mergers will have a very high entropy core. It's a very messy system. You're not going to have low entropy in those systems, low entropy ICM. So that would look like a point in the top right of these panels. So high entropy, but still AGN activity. I don't quite believe that, because I think we should probably see that same signature in the star formation, the H-alpha plots as well. I think if you're driving gas to your black holes, you're also driving into your galaxies, right? It could be that, as a reminder, that we have this system we studied at high redshift Spark 749, where the cooling is not being funneled onto your black hole. So if this is common, if you get dislodged BCGs, perhaps if that's really common, then perhaps you get these scenarios where you have a lot of star formation going on, but you don't have AGN being ignited, right? So that could be a possible explanation for what we're seeing as well. And then finally, I want to talk about was feedback more or less effective in the past? So we talk about how the conditions, the trigger for the cooling and feedback cycle, how has that evolved? Basically, it hasn't. And was feedback more or less efficient in the past? It's the next thing we want to talk about. So we were saying before, we've seen this plot already, but the systems that are most strongly cooling, most efficiently cooling are also like quasar systems. We've said before, quasars are more efficient. Quasars are more frequent as you go towards higher redshifts. So maybe what we're seeing here could be seen in redshift as well. So you might notice in these histograms that the average, I've written here, average redshift of these different chunks of data as well. Average redshift in the lowest bin is 0.06, and as you go up, you have a higher redshift. So maybe what this is telling us is that as you go towards higher redshifts, you're getting more efficient cooling or less efficient feedback, right? So I don't think this is the right sample to study that with, though. This is very extreme systems that I studied in this paper. But we do have just the right sample for this. And that's our SPT Chandra sample that I've already been telling you about. So with this, we have all the X-ray data and that we need, and optical data that we need to be able to make these star formation rate versus cooling rate plots again. And here I'm showing you data from that previous paper, Calzadilla 22, in gray, and the red line here is a fit to those data. And then in green and blue, I'm showing you our new data from the SPT Chandra sample and different redshift bins. And what this is telling you is that this is pretty consistent with not really any change in the slope of these. These are all still pretty consistent with the same kind of steeper than unity slope we see at low redshifts. If you were to measure the average star formation rate, so just basically call, which diagonal lines of these, like which slope one line fits the data best. This is telling you here, if you include upper limits in the green curve I'm showing you here, there's really no evolution in this average cooling efficiency. Right up. Well, my summary slide was moved to the very end, so let me just scroll to that actually. So I've been telling you about how in the most extreme heating systems, so one of my papers on the most extreme heating system, heating is unnecessarily powerful. In extreme cooling systems, feedback struggles to keep up. And SPT-related samples, multi-wavelength data, that we have multi-wavelength data on their spins, a really high redshift, large redshift range. We demonstrate for the first time that the trigger for cooling and feedback, for cooling at least, hasn't changed to high redshift. But it doesn't quite predict radio AGN activity as well as at low redshifts. So that's, I think what we're starting to do is probe the beginnings of the establishment of the AGN feedback cycle with upcoming surveys like SPT3G, for example. We'll be able to probe to lower mass systems and also higher redshifts. And with many other large surveys that cover many different wavelengths, I think we'll be able to actually start answering like when did AGN feedback cycle start on average, and so on. So with that, that's kind of the end of my science, but now it's the most important part of the talk, which is the acknowledgements. So I first want to thank my lovely committee. They've been great, and they haven't fussed at all about my last minute scheduling of things. And I thank you for reading my thesis. I know it's a lot. But in particular, I want to thank Mike. I think Mike has just been, I tell everybody every single time we have an open house of prospective students coming to visit that Mike is an angel. You should definitely work with him. You've all heard me say this before. You know it's true. So Mike has just been incredible. Before I, and our research group has also been incredible. We've had a lot of fun over the years, and there's different iterations of the team, and they've always been supporting me. But yeah, Mike in particular, just really want to thank. I found Mike. I met Mike in 2013. I don't know if you remember this, but you were giving a talk at an REU that I was at at Harvard. And you gave a talk, I was like, this guy's cool, he seems nice. So later on, when I was applying for PhD programs, I looked him up and I was like, are you taking students? Before I even applied, just to see if it's worth applying. And I'm so glad I did. Actually have no, I won't say that fun story. I'll tell you later. But yeah, I'm so glad I did. I think my biggest advice I tell prospective students now is, you want to do cool science, obviously, but choose where you want to go based on your advisor, like based on the fit with your advisor. That's going to make or break your relationship. I think the science is secondary to that. Like science is obviously important, but it's going to be secondary to your relationship with your advisor, your relationship with other grad students, for example. But Mike has been a perfect example of this, and I'm so glad I reached out to him before I applied. And I see Mike as just like a really cool friend that I get to work with, and I hope we keep working more in the future. I want to thank my family who has come here. So my mom and Jonathan and my brother have come from a long way, and they've been pulling up with all my stress over the past few days, but also incredibly supportive over the years. It's really hard to do a PhD away from all your family. I feel like as like a first generation student, like I feel like being the first person that ever left the house and like went to college, and I'm all the way out here, all my family's still out there. It's really hard being apart from them, and it's really nice to see them here, and I want to thank you for all the support over the years, my whole life. My mom was always pushing school, and like you gotta go to school. So she's why I'm here. And this next part is hard. So this is my dad. He's not in any of the previous pictures because so he passed away my very first month of my PhD, and I haven't told many people about that. Very few people know about that. But I feel like, so my dad is arguably what led me to go into astronomy. He inspired my passion for astronomy. He bought me my first telescope. He always liked to talk about space. And I would have loved to have him here today, but I've been trying this whole time to do everything I can and to honor his memory. And if that wasn't enough, my grandma, less than a year ago, also passed away. She was really excited to be here, so I'm really excited she can't be, but she loved talking to me about work as well, like what I was up to, and she was so curious, and she was always curious, and like even in like the past year, I taught her how to make bread. She loved making bread. With the COVID skill we all picked up. A lot of these hardships I want to mention also. Especially when this happened, I was just joined, and Mike especially, but I also want to call out specifically Mike, Scott, Kathy, Jackie Hewitt, John Belcher. They were all tremendous forms of support for me, and they were really understanding and helped me out a lot to process all that and handle grad school, my first semester of grad school. It's been a lot easier with having somebody incredible like my partner Caitlin by my side. We've been together over 9 years, and she's the kindest, sweetest person I know. We've had a lot of fun together. There's a lot I can say. I also want to thank her family, Caitlin's family, for having me as one of their own, and always giving me giving me lots of fun and food and all that stuff. And so the Deutsches. Carol is also in these pictures, and Anne in her family has been another kind of making this home feel like another home away from home whenever we go there for Thanksgiving and all that. And finally, I want to say that I think what's the biggest difference that's been made in grad school for me is all my friends that I've made. So it's after that very first hard year, I feel like having all of you there has helped me through all of that and tremendously. And I once told Mike, I regretted saying it as soon as I said it, but I was like, I feel like grad school is kind of like daycare. We just like go, we just like go have fun, and we have snacks, like we have free like grad lunch. We even like almost made a nap room sometime. We were almost successful, and then we have a meeting with our advisor once a week. It's like so it's just been a tremendous time, and I want to say I think there's a really nice quote I saw. I don't know when it was, but somebody said it on Twitter. It was like, the product of your PhD is you, not your thesis. And I feel like all the connections I've made throughout my time in grad school, I feel like it's made me like a much better person in many different ways. And I will always cherish the memories I made here. And it's sad, it sucks to be leaving, but it's been a great time. And so with that, I'll just leave you again with my summary and take any questions.
Questions? All right, any questions?
questions online.
I think in part 3 you were mentioning that the threshold wasn't explained among like radio frequencies. That might be butchering that. Is that like the next question you're trying to answer when you go to Harvard? Like what's the next thing that you're looking into?
Yeah, so one thing that let me see if I have these backup slides. I'll just go back to that. So yeah, the fact that we can't see this dichotomy anymore. I think there's a lot of reasons for this. The
question is more like, what is that what you're working on next, or like what is it that you're working on or looking to answer?
A variety of things. There's an SBT survey that I've worked on has it's discovered a lot of galaxy clusters, but there's a next generation of surveys, the SPT3G, that are going to have thousands and thousands of galaxy clusters up to even higher redshift, lower masses. And I want to use, for example, machine learning to be able to distinguish those. And let me see if I could find this. Since I have my computer here, I can show you. Right, so a galaxy cluster, as I was telling you about before, they go through these periods where they're really messy, and then they kind of become a lot more relaxed. It's really easy to tell if they're relaxed or disturbed from X-rays. You can see the morphology, how symmetric it is, for example. But the problem is X-rays are really hard to get. It's really expensive to get X-ray observations. There's only very few telescope facilities that can actually measure X-rays, right? So I did this kind of pilot study where I developed some different machine learning algorithms to be able to looking through simulation data, illustrative simulation data, to look at those and measure, and based on the magnitudes that we can measure for all of those systems, and the various labels that we have of like degrees of relaxedness, matching those to the targets, very crudely estimate whether a galaxy cluster is disturbed or relaxed based on just optical data, which is much, much cheaper to get than X-ray data. So that's going to be my first kind of year of my postdoc study. And then other parts are going to be the kind of stuff I said I didn't talk about for the Hubble paper. I'm going to be following that up too. So how do AGN, I told you this whole time how they suppress cooling for the most part, but locally they also enhance cooling. So through a lot of driving all this turbulence is kind of mixing material, and that leads to like, in situ a cooling of material, which I can talk about at further length. But yeah, those are two big things we'll be doing.
So when I look at the way things evolve with redshift, there's interesting trends there, and it makes me wonder: is there any possibility that there's some kind of dependence? I don't know how you would call this out, but as you go to closer to the modern universe, I would imagine the infon gas might have more of a metal content. Is there any way of separating out the role that metallicity of the infon gas can play into the stuff that you're seeing?
Yeah, I feel like more like. There's this kind of residual cooling flows, but then like probably some like line cooling, if that's happening when you have more metallicity in your materials. That could, yeah, you're right. I think how would you tease that out though, like as a function of redshift? Like, how has metallicity in these systems evolved?
So is there evidence for metallicity evolution?
No. So like I think Mike has written papers on this.
I can help at this stage.
Yeah, Mike's written papers on this, and basically lots of things we can measure in galaxy clusters, like the BCGs or the centers of galaxy clusters, hasn't really evolved as far as we can tell. But like, for example, cool core fraction has stayed the same. This metallicity, I think, has stayed the same for the most part. A lot hasn't changed. So looks like we got to keep pushing further and further into redshift, or maybe lower mass, like different parts of the phase space to be able to see any evolution. But so far, we're seeing it's just been chilling for a while.
We were talking about the threshold for star formation. You found that it didn't really evolve with redshift. Was that expected or a surprise, or did people not really know what to expect?
So when I asked this to Mike, one of my first years of grad school, and he was like, we don't really have any a priori reason to expect it to be lower or higher at higher redshifts. But the fact that things are messier at higher redshifts, so you have a lot more gas around, like some, maybe what Scott asked about, line cooling, things like that. There's some different processes could be contributing to like the star formation beyond just the cooling flow. So you have like mergers bringing in gas, and then you also have these residual cooling flows. Those can both be happening at the same time too. So it could have been that maybe whatever threshold we measure would be lower because you have a lot more stuff coming in. I don't know, but we didn't have an a priori reason to expect either way.
Wonderful talk, Michael. I was wondering if you could say a few words on how the future of Chandra might impact how we answer kind of some of these questions.
Yeah. So yeah, it's a really prickly subject, but I of course would like Chandra to stay up. I think it would be really shooting yourself in the foot. It's the only real high resolution X-ray mission that we have right now. Hopefully Axis could also come online. For me, I mean, in particular, just for me, just talking for myself, for my research, I don't think I'll be too strongly affected. The reason I say that is because, for example, when I was telling you about like bubbles, that to be able to measure bubbles to measure AGN energy, right? When I showed you this this guy here, this guy is at redshift of like 0.7, and the bubbles are almost impossible to see. You got to have supporting evidence. As you go to high redshift, you're also the resolution of Chandra isn't the best for being able to see really high redshift bubbles. At low redshift, it's incredible, but I think we've kind of tapped our limit with being able to study studies of cavities with Chandra. For now, I think we would have to get a year of data to be able to get one system. It's just not feasible, right? So I'll tell the story here where I said I would tell you later. But so when I was deciding where to go for my PhD, I got into a couple places at MIT being one of them. I was in Cambridge. I was going to stay there. I was going to work on the Hitomi mission, which I don't know if you've heard about it, but CRISM is now its spiritual successor. But CRISM, yes, Hitomi, launched, and it was great. It was going to revolutionize the study of high resolution of spectroscopy of galaxy clusters. And then a month later, I come and fly and do my visit here, and I'm talking to Mike. In the middle of our conversation, Mike stops the conversation and checks his email. He's like, "Wait, Hitomi just burned itself to death." Hitomi blew up at that time, and it was at that exact moment I decided not to put all my eggs in the X-ray basket. So I diversify. So that's like Michael was saying, and I've shown you here. I studied lots of different wavelengths. For my science in particular, I don't think it'll be the end of the world. But of course, I want Chandra, and I would like Chandra for follow-up of specific objects. And I'm hoping we can get some new missions in the near future too. Yeah.
Can you talk more about the offset between the BCG and the rest of the gas? Like I would expect naively that they'd all be in the same potential level, and you'd expect the most massive things to be overlapping, but it seems like it's not the case, at least for this example. Is that common?
So I don't know how common it is. We have to be able to, so these are happening at this system, for example. You have lots of mergers going on at these higher redshifts. I imagine at higher redshifts it is a lot more common. You have these major mergers knocking your BCGs out of the gravitational potential. In general, these BCGs follow the X-ray peak, but not exactly the centroid, and that's you can also get offsets between a centroid, which is basically the big dark matter average dark matter center, versus the peak of the X-ray emission. That's more of the matter is cooling. Those can be offset all the time, and I don't think those change that much as you go towards higher redshifts either, but we don't know. Yeah, basically.
All right, in the interest of time, we're going to stop questions, but contrary to what Michael said, this is not his last day of work, so he's asking questions for a little while. So let's give him one more round of applause.